today we're going to be looking at polar covalent bonds and polar covalent molecules, or actually polar molecules. And of course, we start off with a picture of bond, because he's going to help us remember. The name's bond, ionic bond, taken, not shared, right? So if we have something like lithium fluoride, our lithium atom has transferred a single electron over to our fluorine atom, and of course that gives us the salt lithium fluoride. On the other hand, we have another situation where we've got nonpolar bonds. So here our difference in electronegativity is essentially zero. Nonpolar, sharing of electrons equally between our two carbons. So here we've got a situation where we're looking at either a carbon-carbon bond versus a carbon-oxygen bond. So if we pull up the electronegativity values, on our CO bond, we've got 2.5 for carbon. Our oxygen has an electronegativity of 3.5. Now our electronegativity, that's the affinity of that atom for its electrons, for electrons in general. It will draw the electrons towards itself the more electronegative it is. So here we have the unequal pairing of these electrons, right? So there's a difference in the electronegativity. So if it's a difference in electronegativity of 0.4 or less, we say that that's a nonpolar bond. That would be like our dear friend here, the carbon-carbon bond. If we have a difference in electronegativity of 0.5 to 1.6, then we've got ourselves a polar bond. And of course, if we go 1.7 or greater, now we're looking at an ionic type of bond. So if we do our math here, 3.5 minus 2.5 gives us a difference of 1. And of course, that's right square in the middle of our polar bonds. You'll notice that carbon, the less electronegative of the two, has the partial positive over it, indicating that the electrons are being drawn away from it, because the oxygen has a greater affinity for those electrons, greater electronegativity. And of course, because it's drawing the electrons towards itself, it's going to end up having a partial negative charge. So you'll notice that the bond starts to pull the electrons towards our oxygen in this case, versus our carbon-carbon bond, where we're going to have the equal sharing of those electrons because it's a completely nonpolar bond. So only when we have the unequal sharing, that's where we say we've got a polar bond. So electronegativity, this is what we're using to figure out who gets the electrons. And as you start off over here with cesium, cesium's got the lowest electronegativity on the whole table. And as we go up and across our table, you'll notice that fluorine has the highest electronegativity. You'll also notice that our noble gases aren't shown. And of course, they have no desire to acquire or let go of any electrons. They have their octet, so that's why they're not pictured. We don't usually say that they have any electronegativity because the majority of them have no desire to bring electrons towards themselves. So you'll notice that our trend, we have the increasing electronegativity as we go across our chart, and we also have increasing electronegativity as we go up our periodic table. So our overall trend is up and across, with fluorine being the highest in electronegativity. Watch out, noble gases are not shown. Alrighty, so this brings us to a couple of examples. And our couple of examples here, we've got a carbon-nitrogen bond. And so if we go back to our electronegativity table and we look up our values, we'll notice that carbon has an electronegativity of 2.5. Our nitrogen has an electronegativity of 3.0. So we do some simple math. So we have a difference of 0.5 in between them. And we said that if it's nonpolar, it's 0.4 or less. If it's polar covalent, it's 0.5 to 1.6. And if it's ionic, it's 1.7 or greater. So in this case, our category is going to be the polar covalent bond, 0.5 to 1.6. So here we go. Our carbon is going to be the less electronegative of the two. And of course, our nitrogen is going to be the more electronegative of the two. So the one with the higher electronegativity is going to be the one where the electrons are going to be pulled towards that atom. All right, in our next example, we can look at our carbon-chlorine bond. So this is another bond that's going to be polar. Again, our carbon electronegativity of 2.5, so now we look up chlorine with an electronegativity of 3.0. Again, we've got a difference of 1.5 in between our two electronegativities. This still puts our carbon as the less electronegative with the partial positive, puts our more electronegative with our partial negative, and again, our electrons are going to be drawn towards the side with the greater electronegativity. In our next example, we've got a CH bond. And so if we look up our values for the CH bond, you'll notice that our hydrogen is going to have an electronegativity of 2.1, and our carbon is going to have an electronegativity of 2.5. So the less electronegative is going to have the partial positive, more electronegative is going to have a partial negative. So this time, it's our carbon that has the partial negative to it. If we look at the difference between our electronegativities, we have a difference of 0.4, and of course 0.4 is usually considered a nonpolar covalent bond, so the equal sharing of electrons. And of course, because we have any difference at all, we're going to notice that there is a slight tendency to bring them towards the carbon, but for all intents and purposes, our hydrocarbons, our carbon-carbon bonds, our CH bonds, we typically think of these as nonpolar covalent, fairly equal sharing. And of course, our last example on this page is going to be a silicone carbon bond. Again, if we go to our table and we look up the values, our silicone is going to be an electronegativity of 1.8 versus our carbon at 2.5. Of course, when we look at these two values, we notice a difference of 0.7. And of course, that fits nicely in the polar covalent category because that's going to be 0.5 to 1.6. So here our silicone is going to be the less electronegative of the two. And of course, that means that our carbon is going to be the more electronegative and that the electrons are going to be drawn towards the carbon in this case. So this is kind of an interesting situation, right? It's sort of the other side of the coin. So we can have carbon attached to things that are more electronegative and the electrons are being drawn away from the carbon, or we can have it connected to something that's less electronegative and the electrons can be drawn towards the carbon. So drawn away versus drawn towards. So carbon is kind of interesting in that way because depending on what you connect him to, he can either be the less electronegative, partial positive, or it could be the more electronegative, partial negative. But in order to have a polar molecule, which is really where we're going with this, is we've got to have two things. We've got to have not only at least one polar bond, there's a second criteria that we need to meet, and that's, of course, asymmetry. So here's an example. This is chloromethane. So we have a tetrahedral carbon. It's attached to 3 hydrogens and a chlorine. Okay, so when we think about tetrahedral, right, we've got a little bit of a dipole coming in for these hydrogens, not much though. Those should really be kind of tiny arrows. Here we've got our carbon-chlorine bond, and of course in that last exercise we just noticed that our carbon-chlorine, our electrons were going to be drawn towards the chlorine. And so we can represent these with dipole arrows. So the electron being drawn towards the chlorine, we make an arrow that points towards our chlorine and we say, hey you're being negative. And of course that's why we're pointing at him, because he's being negative. You can also do a notation where this end of the arrow has a sort of a crossbar on it, and of course that sort of looks like a plus sign. So the less electronegative would have the sort of the plus end of the arrow, and the arrow tip would point towards the more electronegative atom, like this, right? So this would be the less electronegative end. This would be the more electronegative end. And so if we think of this in 3D, right, because after all, our molecules are existing in 3D space. So if we imagine that these dipoles are coming in towards the carbon, and then we have the electrons being pulled up towards the chlorine, this is something we call asymmetry. So it's not pulling the electrons in equal opposite directions or pushing them all in the same direction. Here we've got asymmetry. So some of them are pushing towards, some of them are pushing away. There's a net difference, right? And of course we call that the net dipole. And that leads to an area of sort of partial positive, a lack of electron density on this end of our molecule. And we have a buildup of electron density, or a partial negative, up here by our chlorine, if we looked at an electron density map. And of course, what the end goal here is that we have a net dipole over our molecule. So if we had another one of these molecules, the chlorine end would be down here attracted to the partial positive end of the next molecule. And we're going to see very soon that that has some interesting implications. We can also have polar bonds, but the molecule as a whole may not have to be polar. So watch out for this. So this is what I was talking about, symmetry versus asymmetry. Here we've got perfect symmetry. So even though we have polar bonds, they're pulling in equal opposite directions. So if you imagine that there's a tug of war going on, and each of those electronegative atoms is, one of the tug of war pullers. And at the center atom, there's a rope with a knot in it. And so each of the fluorides would be pulling 120 degrees apart from each other, but that center knot wouldn't move. Remember, this is sp2 hybridized. You have a p orbital that's coming into and out of the plane here. It's trigonal planar. And of course, this is one of the reasons why it's really important to be able to determine the shape of a molecule, because after all, that's going to have implications on whether the whole molecule is going to be polar or not. You got to be able to see it in 3D. Here we've got carbon tetrachloride. So, as we go from trigonal planar to a tetrahedral example, again, if you kind of imagine, a rope with a knot in the center of it, 4 lead ropes coming off of it, if each of those chlorines were pulling with equal opposite strength, the little knot at the center wouldn't be moving, right? So we say that it has good symmetry, and of course the dipoles are going to cancel each other out, and that's of course why our molecule as a whole is not polar, even though it contains polar bonds, right? That's that symmetry that's making our molecule as a whole non-polar. So watch out for that. So if we look at a few dipole moments, and of course, when you were in Gen Chem, you may have done these calculations. Now that we're in Orgo, we're just going to sort of do a brief, just sort of looking at it to sort of determine whether it's got a dipole. So rather than doing the calculations and figuring out the debye, which are, of course, the units that we would give for the dipole moment, we're not actually going to do the math on these. Of course, you would imagine that something like a salt, that would have a very high dipole moment, and sure enough, it does. Because here we've got 2 different charges, so we would expect there to be a large dipole moment there. We can also look at a series of halogens. So as we look at chloromethane, bromomethane, and iodomethane, remember that as you go up the chart, up and across the chart, that you're getting more electronegative. So our chlorine is more electronegative than the bromine, which is more electronegative than the iodine. Sure enough, as our electronegativity increases, so does our dipole moment. So our more electronegative chloride is going to end up with a greater dipole moment for our molecule than the less electronegative iodide. That would give us a lower dipole moment for that particular molecule. Then, of course, we can look at methane and carbon tetrachloride. In our first case, methane, our CH bond, the electrons are moving towards the carbon. But again, this is tetrahedral. It's very symmetrical, and so we have no dipole moment. Our carbon tetrachloride, we just looked at that example previously, and of course that's where our electrons are being pulled towards the chlorines. Again, tetrahedral, very nice symmetry. So even though we have polar bonds here, still no dipole moment. So watch out for that, because if you have good symmetry, you may not see a dipole moment. This brings us, of course, to our dear friends, the alkenes. And so when we find our polar bonds, because the first thing you got to do is find the polar bonds, and then as we're trying to decide whether or not a molecule is polar or not, we need to be able to determine, whether it's symmetrical. And of course, in this case, we have one that's symmetrical and we have one that isn't symmetrical. And so here we've got our dipole arrows pulling sort of in the same direction, right? So if we sort of added them tip to tip, like a force vector in physics, if we added the sort of nose to tail, right? So we took the tail of this one and we put it to the nose of this one and had it come this way. You'd notice that there was going to be a resulting net dipole. If you took those and sort of added them up, they'd come this way. So this molecule is polar. It has a net dipole. On the other hand, if you notice the two dipoles here, they're of equal size. So the difference in the dipoles are equal, and they're in equal opposite directions. So even though they're not perfectly lined up with each other, the result is the zero net dipole between them. And of course, that means that that's going to be a nonpolar molecule. It's going to have a net dipole of 0. So what does this mean? Well, we can look at the reflection of this with our melting points and boiling points. And if we go over and we look at maybe a table where we've got the cis that has the dipole versus the trans, in this case, that has no dipole, you'll notice that the boiling point for the one that has the greater dipole is higher than the one that has the essentially no dipole. So even though they're the same molecular weight, they have the same attachments, they're different in space, one with a permanent dipole, one without. And you'll notice in both of these cases, if you go to the bromo version of this, there's a difference there too, right? So even though there isn't quite as much of a dipole, because our bromo is a little bit less electronegative than a chloride, you're still going to notice that there's a difference as you go from the nonpolar up to the polar cis architecture of the alkene. So kind of cool, right? Kind of cool. So the first thing we want to look at, of course, is as we start to relate our physical properties with our molecular structure, is we want to consider melting points. And of course, the melting point is going to be our temperature at which an equilibrium exists between a well-ordered crystalline state and a random liquid state. So as there's enough kinetic energy to where the little molecules or ions can start to sort of jiggle past each other, it goes from being nice and ordered and crystalline into the nice jiggly liquid state as the atoms start to be able to pass by each other. And if the substance is an ionic compound, the ion-ion forces that hold those ions together in the crystalline state are going to be a strong electrostatic lattice force that's going to act between the positive and the negative ions in that crystalline structure. So when we're talking about ionic compounds, right, there's going to be a large amount of thermal energy required to break up this order structure of the crystal and create this sort of disorder random liquid state. To get them to move past each other, it's going to actually take quite a bit of energy. And of course, that leads us to boiling points. And you'll notice that when we look at boiling points, we also see an additional piece of information. And of course, that is because boiling points are influenced by the pressure. Because after all, as you go to the greater pressures, you're going to have an effect on the boiling point, right? So at higher pressures, you end up with higher boiling points. At lower pressures, you're going to have lower boiling points because the molecules are in equilibrium, right? Going between liquid phase and vapor phase. And so the less pressure, the easier it is to get into the vapor phase. Now this is worth a look because here we've got sodium acetate. And as we look at the melting points of our molecules, you'll notice that this one is strangely high. And of course, that's just because it's a salt. And the attractions are so strong that here we can get it to melt. But if we try to put enough energy for it to boil, it's actually going to decompose. You're going to break those carbon-carbon bonds down before you're going to be able to get it to let go of each other enough to go into the vapor phase. So we call that decomposition. So the ionic bond is actually going to be stronger than the carbon-carbon bonds, and of course that means that our covalent bonds are going to decompose or break down before we actually get it into the vapor phase. Here we've got our carboxylic acid, really nice, strong hydrogen bonding. Again, we're going to have the melting point. It's going to be higher than some of these less polar molecules. Same thing with the boiling point. You'll notice that a lot of times that there's a good correlation between our melting points and our boiling points. The less polar, the lower the melting point, the lower the boiling point. And then as you get more polar, you get to the alcohols, you get to the acids, you're going to have the increase of the melting points and boiling points. Also, as you have the increase of the molecular mass, you're going to notice an increase in the melting points and boiling points. And of course, when we think about intermolecular forces, really we can sort of lump all of our intermolecular forces under van der Waals. And they're all electrical in nature, the same way that our full charges, our ionic charges, as the same way that you have the positive and the negative attracting each other. We have the same thing for our molecules. We just call them van der Waals forces. They're still positive attracting negative. And we put them into three different categories. We have our dipole-dipole forces, we have our hydrogen bonding, and we have our dispersion forces. All right, so when we're looking at our dipole-dipole attractions, and actually hydrogen bonds are a type of dipole-dipole. When we're looking at our dipole-dipole forces, you'll notice that we have attractions between our polar molecules. So in the last section, we tried to determine what was a polar molecule, right? We found examples where we had at least one polar bond and we had asymmetry. Okay, so let's look at an example. Here's acetone. So here we've got the sort of less electronegative side of our molecule. We've got a more electronegative side. Here's our dipole that's coming up through the carbon towards the oxygen. Our oxygen is going to be the one that's going to be more electron dense. And if we take another molecule of acetone, you'll notice that they're going to line up. And of course, as they line up, there's going to be an attraction between the partial negative of the oxygen in this molecule with the partial positive in this molecule. And that is what we call the dipole-dipole attraction. You can also imagine we could do this with that example we had of chloromethane. So again, our dipole was coming up from the carbon through the chlorine, pointing in this direction, having the greater electron density on this side. On this side of our molecule, we had less electron density. And again, the more electron dense is going to be attracted to the less electron dense side. And again, we're going to have that dipole-dipole interaction. Our next type of interaction is going to be the hydrogen bonding. And dipole-dipole interactions between hydrogen atoms bonded to small, strongly electronegative atoms, such as oxygen, nitrogen, or fluorine, and non-bonding electron pairs on other electronegative atoms can result in these hydrogen bonds. So let's take water for example. So here we have an example of an OH bond, right? So we said in order to have hydrogen bonding, we've got to either have an OH, an NH, or an FH, right? Or a hydrogen that can interact with non-bonding electron pairs on an oxygen, nitrogen, or fluorine. So here we go. We've got the partial positive on our hydrogens. We've got a partial negative on our oxygens. And so if you kind of imagine that we've got the attraction between our partial negative and our partial positive, here we go. That's hydrogen bonding. Let's look at another example. Let's look at ammonia, right? Here we've got a trigonal pyramidal rather than the bent shape. If you draw your dipole arrows, they're going to come up through the center of our nitrogen. And again, you've got the more electron dense nitrogen. You've got the less electron dense side with the hydrogens. And of course, you're going to have that attraction between our nitrogen lone pair and the hydrogen there. So hydrogen bonds have a bond dissociation energy of about 4 to about 38 kilojoules per mole. And that's weaker than an ordinary covalent bond, but stronger than the dipole-dipole interactions that we just talked about with acetone and chloromethane. So notice that these aren't actual bonds. These are attractions. So please make sure that you're still thinking of these as attractions and that you don't get this confused with like real covalent bonds. These aren't covalent bonds. These are attractions. And hydrogen bonding is really awesome because it explains why water and ammonia and hydrogen fluoride, they have far higher boiling points than something like methane. And methane, so CH4, so a carbon with 4 hydrogens around it, has a boiling point of like negative 161 degrees Celsius, right? Versus water that has a boiling point of 100 degrees Celsius. So 260 degrees difference in their boiling points, even though even though they have roughly the same molar mass. And of course, one of the most important consequences of hydrogen bonding is that water is a liquid rather than a gas at 25 degrees Celsius. Imagine how different our lives would be if, if you went to go drink, have a drink of water, if it had to be, really, really cold in order for it to be in the liquid state. So there would be huge differences. And of course, if we do calculations to where we sort of take out that hydrogen bonding, water would have a boiling point near negative 80 degrees Celsius. What? And it wouldn't exist as a liquid unless the temperature were lower than that. And that would totally change life as we know it. So this is the strongest of our van der Waals, of our intermolecular forces between molecules that is not ionic. And of course, the weakest is going to be the dispersion forces, or our London forces. So as we look at our London forces, these are going to be temporary dipoles in one molecule that can induce the opposite dipoles in the surrounding molecules. So the average distribution of charge in a nonpolar molecule over a period of time is essentially uniform, or statistically it averages out. But at any given instant, because the electrons are always moving, statistically there are going to be moments where the electrons are going to be a little bit ununiform, that they may be sort of shifted towards one side or the other. And so if they sort of accumulate on one side of the molecule, the consequence of that is this momentary, temporary dipole that's going to occur. And of course, this is what we call London forces, or London dispersion forces. So the temporary dipole induces the dipole in the surrounding molecules, and the temporary molecules, they're going to change constantly, but the net result of the existence is that there's going to be a little bit of attractive force even between these very nonpolar molecules. Now, there's two important factors that determine the magnitude of dispersion forces. And of course, that's polarizability and the surface area of the molecules involved. All right, so let's look at an example. Polarizability. So say, for instance, we take a carbon with 4 iodides attached, carbon tetraiodide, and we compare that with another one, right? So we can imagine that in brief moments in time that maybe the electrons sort of shift over to this side for just a brief moment. So in the next door one, as there's less electron negativity on this side, the one next door is going to be influenced by that. And of course, because this one is sort of influenced, there's going to start to be this attraction just for a moment between the two. So iodides are very large. They have large orbitals, and of course that's why they're more polarizable. So here we've got nice, strong dispersion forces. On the other hand, say for instance we take carbon tetrafluoride. Now here's something that we've got more electronegativity on our fluorines, but it's less polarizable. So if you kind of imagine that the two of these are still going to see each other in space, you're not going to have as much of a difference between the electrons being able to sort of shift over to one side, right? So you're still going to have some attraction, for the dispersion forces, but they're not going to be as strong as for the more polarizable iodides there. I kind of think of this as this is sort of, if you've got some extra pudge, you've got some jiggly, right? You've got those large outer orbitals, maybe you've got or at least know somebody with a couple extra pounds. You can imagine that, if they're bouncing around, you can imagine that those outer electrons are going to jiggle a bit. On the other hand, if you have somebody who has almost 0% body fat, they can jump up and down in very little jiggle. And this is sort of the same idea with our electrons, is that we're not going to see a whole lot of jiggle, so we're not going to see a whole lot of this instantaneous dipole where we've got these much smaller orbitals. And so that's really where we're going there, is that the electrons of large atoms, such as iodine, they're more loosely held. And of course, if they're more loosely held, then they can kind of jiggle around and be more easily polarized versus atoms such as fluorine that are more tightly held and less polarizable. All right, so let's look at surface area. So let's look at pentane versus neopentane. So here we've got two atoms. They're exactly the same molecular formula. The only difference is how they're going to be attached. So in this case, we've got just regular pentane. So we've got all 5 of our carbons in a row. And of course, here we've got the surface area, the greater surface area. So our, we're going to have maybe a momentary dipole where our electrons are going to get just a little bit sort of off to this side. This leaves a little bit positive on this side. The adjacent one is influenced by that. So you have larger surface area, and of course you'd have larger dispersion forces than if you take those same 5 carbons and you attach them all to the same inner one. So it's more spherical. And of course, because it's more spherical, it actually has less surface area. So more branching is going to decrease the surface area, and as you decrease the surface area, you're going to have lower or smaller dispersion forces. So as you get more branching, you're going to have smaller surface area, and of course less surface area is of course going to give you weaker dispersion forces. And of course, if we look up the boiling points for each of these, we'll actually see that there is a difference, right? So even though they have the same molecular formula, here we've got pentane. So boiling point of 36 versus neopentane, boiling point of roughly 10. So 26 degrees difference just because of the difference in surface area. Here we don't have, polarizability difference, right? We're still looking at all carbon-carbon and CH bonds, all nonpolar, essentially. And here we don't have any polar bonds, nothing that's going to give us a dipole. So we're just looking at the dispersion forces, those momentary, temporary, instantaneous accumulations of electrons to one side versus the other. And this is the effect that our surface area is going to have on those. All right, we mentioned boiling points just a moment ago, and of course that's the temperature at which our vapor pressure is going to equal the pressure of the atmosphere above it. And we said that those are pressure dependent. And of course, as you increase the pressure, you're going to also increase your boiling point. So here is we have, atmospheric pressure, 760 millimeters of mercury. That's essentially the same as 1 atmosphere, right? So here we have it just regular atmospheric pressures, right? But say, for instance, we drop the pressure. So if we drop the pressure, we also end up dropping our boiling point. And of course, if you've ever heard of something called a rotary evaporator, or rotovap, in one of the labs, this is of course how that works, is that you are taking the pressure down so that you're affecting that equilibrium, so it's more easy for them to reach the vapor phase at lower temperatures. And so as you gently heat it under vacuum, you can distill it off at much lower temperatures and bring off the solvent without heating up whatever compound is of interest. So yeah, vacuum distillation is a great application for why you'd want to drop the pressure down. And of course, that's going to, depending on how low you get your pressure, that can very significantly change the boiling point of any given atom or molecule. And that brings us to solubility. And that's, of course, the last thing that we're going to look at in reference to our polar molecules and being able to apply this information that we now have. And of course, as we look at solubilities, now normally everybody just kind of goes for the Gen Chem version of like dissolves like, right? So if it's, either a polar or ionic solid, you can usually get it to be, soluble in a polar solvent. Or if you have a nonpolar solid, it's usually going to be soluble in a nonpolar solvent, right? So this sort of like dissolves like. And notice here we're taking solids, we're putting them in liquids, and, that's why we're saying soluble. Now notice how we change our vocabulary. So if we talk about polar liquids, one polar liquid and another polar liquid, like water and methanol, we talk about those being miscible. We can mix those two liquids together and they become all one phase. So they're miscible. Versus if we have, so polar and polar, those mix well or are miscible. Nonpolar, those are typically miscible. But of course, if you take oil and water, one that's polar, one that's nonpolar, those are typically not miscible to a large extent. So this whole idea that there's a correlation between our structure and some of their physical properties, we can actually start to sort of make a few generalizations. And that's, of course, I'm getting ahead of myself. Here's our methanol in our water, and of course they're miscible in all proportions. So here we've got a polar water, we've got polar methanol, and of course we've got the hydrogen bonding between them. And of course, you can put any ratio of alcohol and water you want to together. In fact, this isn't just true for the methyl alcohol with the 1 carbon, but you can also imagine this is true for ethanol, so like alcohol. So like you'd have everything from, like a beer at 5%, or you could have it all the way up to, like vodka or moonshine, which would be in much greater percentages of alcohol. Same thing actually goes with isopropanol. So if you get isopropyl alcohol or rubbing alcohol from the grocery store, you'll notice that you can get it like 90% isopropanol, 10% water. And that's, of course, if you're a diabetic or somebody that's diabetic, you want to make sure that you kill the bacteria. That's probably the strength you're going to use. Or maybe you want 70% isopropanol, so 3 carbons, or and in that case, maybe you just have a cut and you just want to clean it up, maybe not have it sting quite as bad. So yeah, all these 1, 2, and 3 carbon alcohols are going to be fairly well, very well miscible in water. And of course, that takes us to the more grown-up sort of version, right? Is that we can go from saying, yeah, we're going to have this hydrogen bonding interaction that's going to improve our solubility, to, well, what exactly does it take? Like, at what point does it sort of drop off? And so this introduces the term hydrophobic and hydrophilic. And of course, hydrophobic, hydro being water, phobic, fearing. So if you have a phobia of spiders, you fear the spider. So it turns out that our molecules have areas on them that are water fearing. They try to avoid the water. There are other functional groups that are hydrophilic, meaning that they are water lovers, or the friend of the water, or filius, loving, like Philadelphia, the city of brotherly love. So water loving portions, and of course those are our polar areas. So if you imagine something like decyl alcohol, our alcohol at this end, this is going to be the water loving portion of our molecule. And of course this long alkane chain, this is going to be the water fearing portion of our alcohol. So this is the nonpolar area, and our nonpolar areas are going to be hydrophobic in nature. Here we've got a hydrogen bonding, or a dipole. And of course, this is going to be our hydrophilic end of our molecule. And so if we have something like decyl alcohol, in this case, we're going to have the hydrophobic region that is going to sort of completely outweigh the little teeny tiny hydrophilic group. And so if we were thinking about what is this going to be soluble in, we would imagine that it's going to be more soluble in a hydrophobic or a nonpolar solvent than it would be in a polar solvent. And that's true, right? Decyl alcohol isn't hardly soluble at all in water. Versus if you put it in hexane or octane, then of course you could get it to dissolve rather nicely. But on the other hand, you've also got something like a typical detergent molecule, right? So every time you do your laundry, this is what's active in your laundry detergent. So you've got these long nonpolar chains that can interact with the grease and the grime and help to lift that out of your clothes. And then you've got this sulfate group on the end of it, and of course that's what's going to interact with the water. And as we go from a hydrogen bonding hydrophilic group to a full salt, salts are going to be much more soluble in water because our ionic dipole interaction is much stronger than even hydrogen bonding, right? So this interaction with water is going to actually be strong enough that our detergent is going to be able to lift the grease out, sort of make a micelle. So if you kind of imagine a structure with the grease at the center and these nonpolar chains sort of wrapped around it, these hydrophilic polar edges sort of making a sphere. So where on the outside you've got a lot of polar salt edges, and the grease is basically at the center of the sphere. So that's how you that's how detergent cleans your clothes. It's kind of cool, right? And of course, when we say things are water soluble, we had to come up with sort of like a definition of like so if we're going to say it's soluble, so where exactly is that? Where is that line? And of course, we come up with the idea that 3 grams dissolving in 300 mils of water is where we're going to draw the line and say that's where it's water soluble. That means it has to be, reasonably soluble. And of course, you can sort of generalize this to if you have 1 to 3 carbon atoms in a polar group, it's typically water soluble. So we just looked at methane, ethane, isopropanol, or methanol, ethanol, isopropanol, 1, 2, and 3 carbon atoms with an alcohol. Those are all very water soluble. And then, of course, as we get to compounds with 4 or 5 carbon atoms, so like butanol or pentanol, butanol, that it starts to not be too soluble. You'll actually start to see layering if you pour that in with water. You'll get an immiscible sort of 2 layers, like oil and water. And of course, a little bit of that would dissolve in. If you get 6 carbons or more to a polar group, and then of course you're not going to be soluble at all. So let's go ahead and summarize our forces here. We have our full charges, cation, anion, and of course our salts. Those are going to have very, very strong intermolecular forces or attractive electrical forces. Our covalent bonds, those are sort of next in strength. That was why we were saying that the sodium acetate would decompose before you were able to break the ionic bond, as if you heated it up and tried to get to its boiling point. We have our ion dipole. So just like we were talking about our detergent just a moment with that sulfate interacting with water, our ion dipole, that's going to be kind of strong. And the same sort of thing if you were just to put salt in water, that's still a very strong interaction. As we get a little bit weaker, we've got our hydrogen bonding, and of course, that would be one water with another, an alcohol with another alcohol, water with alcohol. These are going to be sort of moderate. And of course, as we get to just dipole, so we talked about the chloromethane, or we talked about acetone. Here are molecules that just have a dipole, not able to hydrogen bond, just have a dipole. And of course, London dispersion forces. These are the ones that are the temporary interactions between typically the nonpolar areas of molecules based on surface area and polarizability. All right, let's do a couple of questions and then we'll look at IR.